Welcome back to the proofs slides. We talked a lot about definitions last time, and we're finally going to really apply those definitions today and prove some interesting stuff. So let's continue with where we were. So kind of the setup for a proof is going to be very similar to what we've seen before, proving that something is valid. You got a bunch of assumptions that you are assuming. These are all on the left side of an implication. And then you're also assuming some stuff that you've proven before. And you're using all of those as your firepower to prove that conclusion that you're trying to get at. Okay? So without any further ado, let's talk about proving a for all. Kind of different to what we did last time. It's going to be everything we talked about in the logic slides, but now we're going to start translating it more to English. All right, so if we have a for all, to prove a statement that has a for all in it, and to prove that that statement is true, there are a few different ways to do it. The first way is called proof by exhaustion, which is just like if you have a very small domain that your for all is ranging over, then just try every single element of the domain. Like you only have, I don't know, if you're, let's see you have p of x, and like you're trying to prove p of x, and the domain is the integers from like 2 to 5. You're trying to prove that p of x is true for all of those integers. Well, just try p of 2, p of 3, p of 4, p of 5, and then if they all work out, you've proven the for all. Does that make sense? So that's proof by exhaustion. Just try everybody. If it's small, that's quite easy. Probably the standard way of doing it, the way that you're going to want to do it most of the time, is universal generalization. So using that rule that we talked about last time. So we're going to have an arbitrary element of our domain. We're going to pick that out and then prove that the rest of the statement is true for it. So that strategy from before. You assume you have some element of your domain. Let's call it A. Assume A is arbitrary, an arbitrary element of your domain. And then prove that p of a is true for that arbitrary element. And then you conclude, if you have both these things, like you've proven that p of a is true for some arbitrary element of your domain, you have not assumed anything special about that a, so it could stand in for anybody, right? So obviously at that point, hopefully, it makes enough sense that it's working out for everybody, right? A could have stood in for any element of our domain, and so it's true for all of them all at once. So that's universal generalization in a nutshell. It's very easy though, like this is kind of hard and difficult sometimes, but if you have a for all quantified statement and somebody asks you to prove that it's false, then you actually have a much easier time on your hands, because what is the opposite of proving that a for all is false? So proving that it's not true that for all x, p of x is true. That's equivalent to, right? You can push that negation inwards and get there exists in x such that not p of x is true. Right? Remember how those flip? It's like the De Morgan's law for quantified things. This is saying, all right, it's false that it's not true for all of them. Then there must be one where it's not working. Okay, you just find something called, not one thing where it's false. Find at least one element of the domain where the predicate is false. That's called a counterexample. All right, so if you can find one of those, then you've proven it false. You only need one element, one good element. Okay, it becomes a there exists. So if for all x, p of x is false, then you got to find some element. Then that means then they're not all true. So there's got to be somebody that's false. That is your counterexample. All right, it ruins the party. So let us get to that in 2 slides. Before we get there, I just want to talk to you first about proof etiquette. All right, this is getting very mathematical, and when you start reading proofs in your book or just in research papers eventually, things are going to look like this. It's mathematicians are very, very standardized when it comes to their proofs. So it's customary, first of all, to start a proof by saying that you are beginning a proof. You just say proof in bold with a period at the end. That's saying begin proof. I am beginning my proof now. I guess mathematicians, they don't like surprises. So after, in between this thing, you prove your thing after the proof sign, and then at the very end, once you're done with your proof, you need to mark the end of your proof to just say that you're done and like brag that you did it all correctly. So what happens after you finish your proof is you give the textual mathematical equivalent of a mic drop. So you put a little rectangle and you fill it in, and that marks the end of your proof. That's like you dropping the mic saying, how cool am I? I just finished my proof. Also, people sometimes also put QED instead, and that is Latin. But most people use the rectangle. It's Latin for quod erat demonstrandum, which was to be demonstrated. It's like, so, and that was exactly what I wanted to show you. So I just did that. My proof is over. Mic drop. Let's go party. Okay, so that is proof etiquette, and I'm going to show you that with an example. But see if you can get this proof first. Get the body of it. All right, so here's an example for you. Please pause the video and try it. So prove the following statement using a proof by exhaustion. So it's a for all. Do you see it? For every integer n such that n is between 0 and 3, but strictly less than 3, then n plus 1 squared must be greater than n cubed. Okay? As a hint, you would probably want to convert this to just plain logical symbols first. Convert it to math from English, and then prove it. All right, so proof by exhaustion is just try everybody, see if you can get that working, and then I'll come back and do it for you. All right, so this is our theorem statement, and we would like to, I guess, first convert it to math so that we understand like what it is really asking. So for every integer n, that's a for all, right? For all n, such that n is between this, then this must be true about it. That just screams implication for me. It's like, for all n, if this is true, then this is true. Do you see how I'm reading it like that? So let me put some parentheses. So if this is true, if n is between 0 and 3, then this is true about it. So n plus 1 squared better be greater than n cubed, and that is my predicate that I'm trying to prove. So for all n, I'm essentially proving this big thing, which could be my P of n. So for all n, P of n, and P of n is this giant thing, that implication. Okay? So now at this point, we just have to try like n being 0, 1, 2, 3, or sorry, not exactly 3, less than 3, 0, 1, and 2, and then if this is true for all of those, then we've proven it for every element of the domain that we care about. You see that? So here's how you do it in the standard style. You start out and you say proof. That marks the beginning of your proof. And usually you say how you're doing it as well after that. You're going to say by exhaustion so that you don't surprise anybody. By exhaustion. And then you begin your proof by exhaustion. So what do we need to show in order to prove all of this? I'll just write down this NTS. You'll see me say that a lot. So what do I need to show to prove this, this statement? I need to show that P of n is true for 0, 1, and 2. Those are the interesting elements of the domain, right? That's n going from 0 to 2. That's what that's saying. So if n is between this, then this must be true about it. So I better show that this statement is true for these elements. And those are the only ones it cares about. All right, so let me show P of 0 is true, P of 1 is true, and P of 2 is true. So P of 0, why is that true? That's true because, well, just plug it in. Plug in 0 for n, so 1 squared is, let's see here, 1 squared is bigger than 0 cubed, right? Because 1 squared, which is just equal to 1, is greater than 0 cubed, because n is 0 right now, which is 0. And of course 1 is greater than 0. So that proves P of 0. P of 1 is true because, well, you plug this in again for it. Let me erase. Then you have 2 squared, so that's 4. Because 2 squared equals 4, that is bigger than 1 cubed, because 1 is n right now, which is just 1. That's P of 1, and then P of 2 is the last thing I need to show. And then I will have proven the for all at that point. P of 2 is true because 3 squared, which is 9, is bigger than 2 cubed, which is 8. Okay? And then after that, it kind of blows up, so that's why we kept our range so small. But it works for that range, and that proves our theorem. So we're done. We get to have a little mic drop now, and I will use the rectangle. I'll fill it in, and so that is our first English-style proof. All right, please yell at me in office hours if that didn't make enough sense, but that was what we wanted to do. So we found a very small range. We proved our theorem for all elements of that range, and that proves the entire statement. Isn't that beautiful? Magical. All right, here's another example for you. So find a counterexample. So this is this idea. to prove a for all false, find a counterexample to show that this statement is false. Okay? If n is an integer and n squared is divisible by 4, then n must be divisible by 4. Can you find an example of n where this doesn't work out? Okay, so try that. Maybe convert it to math first again. Pure logic. Alright, so here is my statement. So if n is an integer, so for every integer, and n squared is divisible by 4, so if that's true, then this is true. Do you see how there's another hidden implication? So for all n, if n is an integer, I'll just write n integer, and n squared is divisible by 4. Do you remember that syntax like that? So if all that's true, then n is divisible by 4. Okay? That's the idea. So, let's see if we can find a counterexample. So first of all, this is our predicate. So for all n, all this stuff is supposed to be true, right? So that's our p of n, essentially. There's our p of n. For all n p of n, this is trying to be, somebody's trying to prove this, but they're wrong. So we need to find a counterexample. Find an n where this, like, this all works out. That n is an integer, and n squared is divisible by 4. But that number itself, that original number, is not divisible by 4. And if you think about it long enough, just keep trying them in order, the answer is n equals 2 is the counterexample. Do you see that? N equals 2 does not work. So that's our counterexample, and let's prove that this is really the answer. All right, so first of all, we need it to be an integer, and for its square to be divisible by 4. So first of all, 2 is an integer. It's an integer. Is it divisible by 4 if you square it? Yeah, n squared, which is equal to 4, is divisible by 4, right? Because you can find some factor to go in, and it's just 1, right? Because 4 times 1 is equal to 4, and that 1 can be your k. That proves that it's divisible by 4. And then we need to show that the original number is not divisible by 4, right? So n, which is 2, right? Our example is 2. So n is 2. That is not divisible by 4. You can mark that with a little slash between this, just like you can say that something's not equal to something else by putting a slash between the equal sign. So this is saying n is not divisible by 4 because let me spell that slightly nicer. Because you can't find a multiple of 4, that's a whole number, right? Excuse me. That equals 2, right? 4 times k. 2 is supposed to equal 4 times something. Excuse me again, sorry. So 2 is supposed to equal 4 times something if it's divisible by 4, and that's just not possible for any integer k. Okay, and that shows you that, like, you had all this set up and it was supposed to be true that n was divisible by 4, but no, all this first stuff was true, but it was false in the end. I hope that makes enough sense. And then for divisibility, we're just following these definitions, okay? So x divides y if you can find some multiple of x, multiply it by some k and create that y. Okay, so that's what we were arguing here. We could not find anybody. You would have to pick 1/2, right? The only thing that solves this equation is 1/2, and that's not an integer. Okay, so that's a counterexample. We had the hypothesis, but the conclusion did not follow. So that's how that works, and that's proven for all. So the 2 examples of proving for all. Let's talk about proving a there exists now. So if you have a statement and it has a there exists in it, usually it's a lot easier to prove it. You have something that looks like there exists an x such that p of x is true. If you have a there exists statement, then you only need to find one good, nice element of your domain where you can prove that conclusion. All right, that's all you need. And you can either give that value explicitly or just show that it has to be there somewhere. All right, so here's the proof style. It's like you have some element in your domain. It could be arbitrary, it could be particular. A is in your domain of P. You have that. And then you prove that P of A is true for that one special A. And then you show, you have just shown that there is somebody. There exists an X. It could be A, right? A is an example. There exists an x such that p of x is true. All right, so that's the idea. That's how you prove that there exists. If you'd like to disprove that there exists, now suddenly you have to do extra work. It now becomes a for all, right? Just like if you were trying to disprove a for all, it became a there exists. Now we get the hard direction. So if you are trying to show that there exists p of x is false, there exists an x such that p of x is true, then it must have been the case that you can't find any x for which p of x is true. So that means every element of the domain must have been false when you plugged it into p. So now that becomes a for all, right? So the negation of there exists an x such that p of x is true becomes for all x. It must be the case that p of x is false. Crazy, right? So that's the idea there. That's how you prove and disprove that there exists. So let's try it. All right, so here's an example for you. So prove the following, where n1 and n2, they're just integers, just whole numbers. Prove that there exists an n1 and there exists an n2, just integers, such that n1 plus n2 is equal to 5. All right, there's definitely a few ways to make it work, yes? So give that a try and try writing it down. Here's how I'll do it. So proof, right? You start off your proof and you're like, all right, I have to find two good numbers, two good integers, such that when I add them together, I get 5. It's a very easy proof, right? But it's good to help us walk through the motions of doing it, all right? So, all right, I need a good value for n1 and I need a good value for n2. And once I have those, I just need to show that this works out. And then I've proven my theorem, because this is my little predicate, right? P of n1 and n2 together kind of thing. Does that make sense? So, all right. You can pick 2 and 3, 1 and 4. Let me get crazy. Let n1 equal -2. This is a potential solution, right? And that forces n2 to be 7, right? Let n1 be -2 and n2 be not -7 but +7. Then you just have to show that the predicate is true for them, that the body of it all is true. Then n1 plus n2 is equal to 5, and that's what you needed to show to prove that there are some integers that add up to 5. There are quite a few, infinitely many, but we only needed one. There exists. Okay? You see how that is all following from the definition of everything. If you go back to the logic slides, it's following from that existential instantiation or existential generalization rule, which is essentially this. So there exists is a bit easier. You just need to find one good element of your domain for each there exists. All right, try this one. You don't have to actually prove it. It would be a little bit fancy, but show what needs to be proven in order to show that this existential statement below is false. So we're trying to disprove this, all right? Trying to disprove that there exists a negative integer such that it is equal to its square. That negative integer is equal to its own square. Okay, which we know is not true if you think about it long enough. So we're trying to disprove this, all right? See if you can write in math what needs to be proven in order to show that it is false. All right, so here's my thought. We're trying to show that this is false, which means we're trying to disprove it, which means we're trying to show that its negation is true. All right, so there's a hidden negation in there. And now we'd like to make this less English and more math. All right, so we'd like to negate this. There exists, right? There exists a negative integer. Let's call that integer I. There exists a negative integer, so there exists an I such that I is negative, right? I is less than 0, and it's equal to its own square. So, and I squared is equal to 1, or is equal to I, sorry. Or you could say I is equal to I squared. Either way works. So that is, this part right here is the inner bit. That's the text here, okay, the black text. And we're trying to disprove it, so we're trying to negate it. That's where the negation comes into play. And so now we just need to show what needs to be proven. So let's move in this negation. Technically, this is a valid answer. This whole thing is a valid answer, but we can push in this negation further and make it a little bit cleaner to work with. Okay. So I hope that you notice, like, it's if you read it and think about it long enough, there is no negative number that becomes its own square when you square it, because once you negate a number, the negativity goes away. Yeah. So let's push this negation inwards. So if you push a negation over there exists, you get it for all. So for all I, and then you negate the inside. For all I, it better not be the case that all this is true. And I is equal to I squared. And so now we have normal De Morgan's rule. We can push this inwards again, so we negate both sides, and this becomes an OR. Remember that? So for all I, we have that it's not true that I is less than 0, or it's not true that I is equal to I squared. And we can push those negations in once more because we know how to negate our, not conditionals, but we know how to negate our comparisons like this. And we also know how to negate inequality. Same slide, right? So once and for all, this is finally the simplest thing that we could prove. So for all, we need to show, in order to disprove this, that for all integers I, either I is, what's the opposite of less than? It's greater than or equal to. Either I is greater than or equal to 0, or I is not equal to its own square. Okay? Which seems a bit weird. It's like either it's greater than or equal to 0, or it's not equal to its own square. But that is really the equivalent of this statement. Okay? And so that's what you would go and prove now to show that this black text, this original statement, was false. Okay? I hope that makes enough sense. And now I think we're ready to get into the actual meat of proofs. This was just mostly following definitions. These examples were mostly just following definitions of things. I want to teach you how to prove a conditional statement. All right, because that's going to come up forever. All of these had conditionals in them. Well, the ones that had for alls, at least. Here's a conditional, an implication. I would like to show you how to prove an implication without having to resort to truth tables. And that's very important once you start getting to English-style proofs. Okay? So the one way to do it, the most standard way of proving an implication, is to assume the hypothesis and then prove the conclusion, right? So a direct proof, and the style of this is called direct proof. A direct proof is when you prove that a conditional statement that looks like P implies Q, if P then Q, is true, all right? This is, most of your proofs from now on are going to look like this. And the strategy is, remember what this is trying to say, right? If P is true, then Q is true. That's what that's claiming. So what we do, the way we prove this in just English, is we assume that the hypothesis is true and then prove that the conclusion is true. If that all works out, then the original implication was true. The original if P then Q conditional statement was true. And so let me first prove to you, using a truth table, at least for once, that this is valid, that this all works out. Okay? So let me show you. Let's try all the possibilities for P and Q, and then P implies Q. And I'll show you why this proof strategy is valid. So we got our true, 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 false. Let me write that a little cleaner. True, 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 false, false, true, false, false. And now that I have these, what's the implication? Well, it's true everywhere except for right here, right? And that's when you had the hypothesis but didn't get the conclusion. That's when Dad lied to you, right? So, all right, let me show you that this is a valid proof strategy. Because we're trying to show, right? We are trying to show that this is true, that this statement is true, right? So we need to show that we're in one of these cases. Does that make sense? I'm trying to show that we're in one of these cases. And first of all, we can kind of knock off the P is false case, because if P is false, like no matter what, the conclusion is true. Okay? So the way that we show that this whole thing works out, we just need to show that we can't make it here, because that's the one time the implication is false. We just need to show that we cannot get to this one state. The rest of the states are fine. Does that make sense? This is why this works out. So we just need to show that we can't get here. Show we can't get here. All right? The second we can't get here, that means we must be in one of these other cases, and the implication was true. So that works out just fine. So here is why this works. Assume that the hypothesis is true. So that means P is true. Assume P is true. That means we're in one of these two cases, right? If we assume that P is true, we need to prove then that the conclusion is true. Prove that Q is true. You see how there's only one case where P is true and Q is true, and that leads us to the true statement, right? As long as we can show that the conclusion is always true when the hypothesis is true, that is showing that we've avoided this case. We've avoided the case where the conclusion is true and we've avoided the case where the hypothesis is true and the conclusion is false. And that's the one place that we should not be allowed to get if we're trying to claim that the original implication is true, right? So showing that we can't get here is as good as assuming the hypothesis is true, so we're in one of these two, and then proving that the conclusion is always true, which forces us into this case, proving us that it's true, right? And if the hypothesis is false, we get it for free anyway, right? So that's just showing. That's how you do it. That's how you show that you can't get here, and that is a valid proof strategy. And now we can just use it. If we ever have an implication, we just assume our hypothesis is true, and then try to prove that the conclusion is true. If that all works out, and we can get at our conclusion, then we've proven the original implication, all right? I promise this will make a bit more sense with examples. So let's go straight to an example, all right? So let's prove that this is a true statement using a direct proof, right? So if x is an even integer, then -1 to the power of x is equal to 1. Okay, so first of all, let's translate this to math. Let's see here. Before I get to for alls, do you see where, like, what is P and what is Q? Because we're trying to make it look like this. This is an implication secretly. What is P and what is Q? It's like if then, right? There's an arrow going on. So this is the P, right? X is an even integer. That's our hypothesis. So that's our P. And then we're trying to prove this conclusion about it. That's our Q. All right, so that's our P and Q. And we're trying to prove all this stuff. So we're trying to prove that for every integer x, if x is even, then I'll just write it like this, x even. If x is even, then -1 to the power of x, that even number, is equal to +1. Because they kind of cancel out, right? So that's our proof. That's what we're trying to show. This is our real theorem statement converted to math. And so now let's go and prove it, all right? So proof. So I'd like to prove for every x this is true. So I guess the first statement, the first idea is to like get rid of the for all with this idea of picking an arbitrary element. So like assume that x is arbitrary. That's kind of implicit in a lot of these proofs. So assume x is arbitrary. And then I also need to assume that the hypothesis is true. So assume that P is true about that x. So assume x is an even integer, essentially. Assume x is an even integer. You see how that gets rid of both the for all, because I now have my arbitrary element, call it x, and then I've also gotten rid of this hypothesis. I'm assuming it now. Assume x is an even integer. All right, so now I have that as an assumption, and now I need to go and show that the conclusion must be always true, okay? So assume x is an even integer, and now I have to end up in the case always that -1 to the x is equal to 1, all right? And if you ever get stuck, here's the secret. Use whatever information you have. Like I only have one hypothesis right now, it's x is even. Use that. Unpack it as much as humanly possible using our definitions. Go back to the definition if you ever get stuck. I promise it'll help. So x is even means like this all happens, right? I have some k such that x is equal to 2 times k. That's what it means to be even. So let's go to the definition and unpack that. And that will give us some firepower to prove this conclusion, all right? So I'm assuming this. Now I need to show that the conclusion is true, that Q is true for it. So let's unpack the evenness. So x must be equal to 2 times k for some k, for some integer k. That's what it means to be even, going back to the definition. All right, so now let's see if we can prove it now. So we need to show, right, our conclusion, that -1 to the x is equal to 1. So I need to show that -1 to the x is equal to 1. But what's -1 to the x? I have some information about x now, don't I? I know that it's an even number. So that means x breaks down into 2 times k for some k. I'm not sure which k, because it's supposed to work for every even number, but it's some k. It could be a different one each time. but I can replace that. It's an equality. So negative 1 to the x is really negative 1 to the 2 times k. And do you see how you can make this 1 now? Remember your power rules? This could be brought inwards like this. You can bring the negative 1 to the 2 and then take that to the k. That's how exponents stack up. You can multiply them, or you can make them separate like that. So that's equal. And now what's negative 1 squared? Ooh, that is 1, and then I still have to the k, and 1 to the power of any number, any integer, is just 1. And so look, I started with negative 1 to the x, and I ended up with 1. That was what I needed to show. I assumed my hypothesis was true and showed that my conclusion was true. And I know that's a valid way to prove a conditional statement. With that period is my proof. So mic drop, I'm done. Isn't that nice? So it's okay if this is still a bit fuzzy in your mind. More examples is the only way to make this make sense. But I promise it will with enough of them. Okay, so I have some things that I want you to try first, and then I'll show you my solution, okay? Please try them though. So here's another example where you'll use a direct proof. So again, assume the hypothesis is true, prove that the conclusion is true. So the sum of an odd and an even integer is odd. Show that that is a true statement using a direct proof. So figure out what the hypothesis is, figure out what the conclusion is. There will be an implicit for all. Think about that, and then prove it. And then I'll do it after you unpause. Excuse me. All right, so the sum of an odd and an even integer is odd. So let's convert this to math first. So like, I know that x is odd, and I know that y is even. Let's call these numbers x and y. So I know that x is odd and y is even, and if this is the case for both of those numbers, if x is odd and y is even, then the answer is odd, right? Their sum, x plus y, better be odd. See how I made some variables to help me here? And there was an implicit if-then statement. So the sum of an odd and even integer is odd. So like if I have two numbers and they are odd and even, then their sum is odd. Okay, and I just made up some variable names, so I also need to quantify over them. So where did x come from? Where did y come from? Could they be anything, something specific? They're supposed to stand in for any integer, right? So for all x, for all y. If x is odd and y is even, then x plus y is odd. That is the equivalent in math of this statement. Okay, that's something you'll get better at as you get more practice. So now you can see pretty clearly that here's my hypothesis. I'm going to assume that x is odd and y is even for some integers x and y, and I'm going to show that x plus y must be odd. And hint, hint, the secret is going to involve unpacking the definition of even and odd again. Okay, so proof period. Let's see what happens here. So assume, right? Assume x is odd and y is even. That's the left-hand side. That's my hypothesis. So I assume that that's true and use that to show the conclusion is true. Assume x is odd. I'll just say x odd and y is even. And now it's my job to show that x plus y better be odd. All right, but to get there, let's unpack the definitions of odd and even. Going back to this stuff way up here. Okay, so I've got my evenness, I've got my oddness, and those are my hypotheses. So let's get as much out of them. Let's squeeze as much out of them as we can. So x. So if I know that x is odd, so x better be equal to 2k plus 1, right? So that's what it means to be odd for some integer k. For some int k. And then also y is even. Also, y better be equal to 2 times, it's not the same k. It could be something different. Like it doesn't have to be like, x doesn't have to be 12 and y doesn't have to be 13. It could be some other odd number. So y is equal to 2 times some other variable. 2 times m for some integer m. Okay, so that is us unpacking the definitions, and let's see how far that gets us, all right? So what we need to show is that x plus y is odd, all right? So let's, to show. So x plus y is odd. What does that mean, though? How do you show that something's odd? Well, you show that it's equal to 2 times something plus 1. Show that there's 1 left over. We need to show that x plus y is equal to, I don't know, 2 times some other variable, 2 times r, plus 1 for some integer r. If I show that, then I've proven my theorem. Okay, so that's what we need to get at. We need to figure out that x plus y is odd. And now let's try and do some math. So x plus y, what do I know about x and y? Well, I know that x is equal to 2k plus 1. And I know that y, add that to y. What is y? It's 2 times m. Can I do some math to make this look like 2 times something plus 1? I think I can. Get the 2's by each other. This is equal to 2k plus 2m plus 1. What's that? But I can bring out a 2, right? 2 times k plus m. Ooh, plus 1. And I was just looking for some integer that multiply it by 2 and add 1, I get x plus y. I just found that integer. Do you see that you could pick your r? Like I needed some r. Make this r, k plus m. That's still an integer. To add 2 integers together, you get an integer. K plus m, call that r, and that is showing that you found an integer such that it times 2 plus 1 is equal to x plus y. Because here's x plus y on the left here. Isn't that nice? So that is proving our conclusion. Therefore, right, based on that idea, that's the definition of oddness. Therefore, x plus y is odd. Mic drop. QED. Oh yeah. So that is a fun little proof. I hope that you got most of the way there. Keep trying them. All right, here's a new one for you to try. Do as much as you can until you get stuck, and then I will show you how I do it. But here's the statement. I want you to prove it with a direct proof. So for any positive real numbers, x and y, x plus y is greater than or equal to the square root of xy, all inside of that square root. So this is a little weird because you don't really see an if-then statement just yet. So you have to find that. And before you get started, let me show you what a real number is, just in case you've never heard of it before. But a real number is a number with decimals inside of it. Okay, so decimals are okay. Real numbers, an example of a real number is like 3.14, for example, is fine. That is a real number. Negative 3.14 is also a real number, but we're only caring about positive ones. So let's just forget about that for now. But that's what it means to be a real number. All right, so convert this to math and then go and prove it with a direct proof. So there will be a hypothesis. You'll assume that, and then there will be a conclusion. You will prove that, and that will prove the entire statement. Isn't that cool? So yeah, let's convert this to math, assuming you gave it a try. So for any positive real numbers, call them x and y. So there's some quantification going on. So for all x, for all y, quantify over all of those. And then, did you notice where the hypothesis comes into play? Where's the if-then statement? It's like, assume x and y are real numbers, but they better be positive for this to work out. So if x and y are positive, then you have this conclusion true about them. That's where the direct proof lies. Okay, so if x and y are positive, x greater than 0 and y greater than 0, if that's true about them, then I should probably, to be precise, I should use extra parentheses. If that's true, if they're positive, then this conclusion is true about them. X plus y is greater than or equal to the square root of x times y. Close my little parenthesis. So the strategy for proving this is usually to go left to right. So we want to knock off these for alls, we want to get rid of the quantification, and then we have a hypothesis that we'd also like to then assume. So we'll assume that. Like assume these are arbitrary, assume this, and then prove that. So that's going to be our strategy. Well, let's write that down. It's usually always from left to right like this. So assume that x and y are arbitrary. I've been doing that kind of implicitly, just like assume x and y are odd and even. That's taking care of the assume they exist, as well as assume in addition that they're odd and even. So technically you can talk about that idea separately, because that's how you get rid of the quantification. So assume you have arbitrary x and y's, they exist, they're elements of your domain, they're real numbers, and then furthermore assume that they're positive. And then if that's true about them, then it must be the case that you do this weird thing and it works out. All right, so assume those are true, and then we have a direct provable thing. We have a hypothesis that we will assume, so assume this. That's our P. Assume this. And then we will prove the conclusion with that. So prove this. Okay, so that's the idea, and let's get at it now. So if I want to prove this, I'll say proof. And I would like to assume x and y, assume that they're positive, and then show this. Okay, so let's write all that down. So proof. Assume x and y exist, they're real numbers, and they're positive. So assume x and y are positive. That kind of takes care of both of these at the same time. You see that? That's how you can do it in English pretty quickly. Assume x and y are positive. Well, you should always be thinking about the actual rules that we talked about in the previous slides. Assume x and y are positive. And what do we need to show now? So we've assumed this, we've assumed that. We need to show the conclusion. So what we need to show, NTS, is that conclusion, x plus y is greater than or equal to the square root of x times y, which looks really weird. And there is a trick involved with math to get this closer to what you want it. So assume x and y are positive. We know something about that. And then it's going to involve, like, how do you introduce a square root usually? You have something squared before that. So squaring should be on your mind if you got stuck and you want to try it now. That's your hint. You have to square something. And the idea is going to be like, if I had x plus y squared over here and I had just xy over here, I could take the square root of both sides. And then I'd end up with this. So let's see if we can start out with that. All right. So here's going to be our little secret. All right. So here's the hint. You kind of have to come up with this. If you think about it long enough, this will be your starting point. But let me show you that it works. So x squared plus xy plus y squared. I know that that's positive. Let me show you why. So what do we know before all this? We know that x is positive and y is positive, so that's x is greater than 0. It is a bit of a trick to like think of this first, but I'll show you how you could have thought of it. It's like going to end up being x plus y squared, and like square that too, bring them all to one side. So I know that x is positive, and I know that y is positive just by assumption, right? From those, if I square both sides, like I multiply with this by x on both sides and multiply this by y on both sides, I end up with knowing that their squareds are also positive. That'll be helpful. X squared is greater than 0, y squared is greater than 0. And then I also have xy in here, and I promise that is necessary. What do I know about xy? Is that positive too? Well, yeah, because you got to remember your algebra rules, but if I multiply by this equation by y, or this equation by x, I end up with xy greater than 0. So I know all those things at once. They're all positive, and if I add a bunch of positive things together, right, I know that xy is positive, x squared is positive, y squared is positive, x times y is positive. If I add together a bunch of positive things, it's still positive. Ooh. So that's the start. And now I want to start making this look like this, but the squared form. So let's like get xy over here, let's get x plus y squared over here. Let's figure that out. So let's transform this a little bit. If I add xy to both sides of this equation, here's what I end up with. I have x squared plus, if I add xy to both sides, right, then I have 2xy on this side, and then I have another y squared, and then greater than not 0 anymore because I added xy to both sides. This is the same as the original equation, right? We started with this, and then I added xy to both sides, same equation. But what is this left side now but x plus y squared? Isn't that nice? So that is equal to x plus y squared, and that's kind of where the secret lies. You had to come up with that idea. You had to think about that. That's greater than xy, and now this is just a square, take a square root of both sides away from being very close to this idea, okay? X plus y squared is greater than xy, and so now if I take the square root of both sides, I get that x plus y is greater than the square root of x times y, and that's essentially the conclusion, right? I need to prove that x plus y is greater than or equal to the square root of x times y. But if I know that it's strictly greater than, like, it's a weaker statement to say that it's greater than or equal to, right? So automatically, just from that, from knowing that it's strictly greater than, it's positive. If you subtract, I guess, it's positive. If you have a strictly greater than, you know that it's also greater than or equal to, right? You just know it wasn't equal to begin with. So we're kind of losing some information by going here. So technically, I could have just proven that it's strictly greater than, but the proof wanted greater than or equal to. And so that works out just fine. And so what do you know? I have this thing that I needed to show by starting with this, and it took some thought, but just these two ideas, just knowing that x and y are positive, gave us all of this. And then bringing them together, we start with this inequality and end up with enough magic to right here. Okay, so that's the secret. You'll have to go off and think for a while about some of these proofs, but they all do come together. We found some arbitrary x and y's, we assume that they're positive, and then we proved this conclusion. Okay, so hopefully with enough examples, it's starting to make a little more sense in your head why you can do all this. Assume the hypothesis, prove the conclusion. But that's direct proofs. They're going to be, there's a reason I'm doing 4 of them in a row with you. They're going to be super, super important for the rest of the semester, okay? And for the rest of your computer science career. So let's have another one. So again, I want you to try this as much as you can, and then I will take over and you can press play again, okay? So how about this one? The average of 2 odd numbers is an integer, which is not immediately apparent, right? Because maybe it's you have 2 special odd numbers, you bring them together and you take their average. Maybe it's like got a 0.5 involved there. That's definitely possible. So let's prove that that's not possible. Let's prove that whenever you have 2 odd numbers, if you average them together, you end up with an integer. All right. So first of all, this is a direct proof. Do you see an if-then statement in here? That's going to be the first trick. So convert this to pure math, convert this to logical symbols, and try and prove it. All right. So here's how I would convert this to symbols. So I have 2 odd numbers. Let's call them something. Let's call them x and y. So for all x, for all y, if they're odd, there's your conditional. If they're odd, that's your side condition. If they're odd, then their average is an integer. It's kind of mixed up in this English sentence, but if you think about it long enough, it needs to look like this in logic. So if x is odd and y is odd, if they're both odd, then I know that their average better be an integer. So x plus y over 2 is an integer. I'll just say int. All right, so that is my theorem statement. That's what I want to prove now. Okay, so proof. I'm going to assume x is odd and y is odd and try and show that their average is an integer. Okay, so let's, again, whenever you're stuck, unpack that definition of what you know about your hypotheses. So assume x is odd and y is odd. That's going to be my first my first sentence in this proof. So let x and y be odd numbers. Odd integers, I guess we could say. So that's taking care of this. Like I've gotten rid of the quantification and I've gotten rid of the hypothesis. Now all is left. All that I need to show is this conclusion. Okay? So I need to end up with that. But let's unpack the definition of odd first, because that'll help us. So I know that x is equal to 2k plus 1, right? That's what it means to be odd. And then y is also odd. Y doesn't have to be equal to also 2k plus 1. It could be some other number that's also odd. So y is equal to 2, I guess I use m next, 2m plus 1. And k and m could be any integers. For some integers, k and m. Okay? And now, let me take the average of x and y. So x plus y over 2. I know what x and y are now. They're these things. Let's use that. So x plus y, which is really equal to 2k plus 1. Let's write it like this. 2k plus 1 plus 2m plus 1. Over 2. Can I simplify that? I can get these close to each other again. 2k plus 2m plus 2 over 2. What do we got here? So that is going to be, if I get rid of a 2 on all of these, I can totally divide this top by 2, right? It's k plus m plus 1. K plus m plus 1. Okay? And now all I need to show is this is the result, right? This is the result of taking that average of those two numbers. I just need to show that this result is an integer. Is it? Of course it is. So k plus m plus 1 is an integer. I want to say int, because, why? Well, because I just assumed that k and m were integers, right? If I add two integers together, it all works out. Because k and m are both ints, if you add an integer and one is definitely an integer, if you add a bunch of integers together, you end up with an integer. So the oddness kind of canceled out when you brought them together and you averaged them. You ended up with an integer. Could be odd, could be even, doesn't matter, but it's a whole number, which is beautiful. All right. So k plus m plus 1 is an integer because k and m are both integers, and 1 is, of course, also an integer. I don't think we need to say that. All right. So therefore, what is k plus m plus 1 but that average? Therefore, x plus y over 2 is an integer. Did you get that? So we're just unpacking all those definitions that we got for free based on our assumptions. And so that's what we needed to show. We assumed all this stuff. We proved this finally. That's what we needed to show. Mic drop, QED. We are done with our proof. Isn't that lovely? So that is direct proof. That is usually how you're going to prove a conditional statement. You're going to assume that the hypothesis is true and prove the conclusion. I do want to show you, before we go, I'll have you try an example next time. I want to show you another way of proving an implication. It's going to end up being a direct proof again, but we can flip-flop things, and that sometimes makes it easier. All right. So do you remember the contrapositive of a implication? So if you have P implies Q, that is equivalent, right? I showed you this. That is equivalent to swap the hypothesis and the conclusion and negate both sides and keep it an implication. So P implies Q is equivalent to not Q implies not P. Remember to swap those things. Those are equivalent. And so if this one was hard, if this way was hard, sometimes if you flip them like this and you make the contrapositive, it's an easier proof, but it will still be a direct proof. It's just now you're going to assume this and prove that. See that? That's the idea. Let's see. Or maybe I didn't prove to you that the contrapositive is equivalent. Let me do that for you now. I guess there's a reason I'm reminding myself to do it. Let me show it to you now. P and Q, and P implies Q, and then I'll do the rest in just a second. So P is true, Q is true, true, false. Let me just show you that this is equivalent to its contrapositive. False, true, false, false. So P implies Q is, of course, true, false, true, true. We should know that by heart now, probably. And then I need not Q and not P, so I could make an implication out of them. So I need not Q, I need not P, and then I need to create that implication. Not Q implies not P based on that. And so I just need to check that this is equivalent to this, and that will end up being the case. So not Q is false, true, false, true. Not P is false, false, true, true. And then their implication is false implies false, that's true. True implies false, that's the one time it's false. False implies true, that's true. True implies true is true. And what do you know? These are equivalent truth tables. So they are equivalent logical statements. So just in case I didn't show you before, I forget, that the contrapositive is equivalent to the original implication. Now you know, all right? So now I could just as easily prove this one instead of this one, and it will have been worth the same amount. It proves the same statement, it just looks a bit different, okay? And then we can also do this using our equivalence rules, which is slightly easier. P implies Q, that's equivalent to not P or Q, right? Which is equivalent to Q or not P, which is equivalent to, I just use commutative law there. I can also do double negation on Q, not Q or not P, that's the same. And then what do you know? If you have a negated something or something else, that's an implication between those two things. So that's equivalent to not Q implies not P. So that's slightly faster in my opinion. So if you have an implication, you could flip it around, negate both sides, using this contrapositive idea and prove this instead using a direct proof. So assume not Q is true, prove that not P is true. Sometimes that's easier than assuming P is true and proving that Q is true. Okay? It's the same idea though. It proves the same thing, the same theorem. It just will look different, and maybe it will make a bit more sense and it will go through easier, right? So we'll come back next time in the next lecture for this week and prove our first contrapositive theorem. But again, it'll be a direct proof. We just need to flip-flop some stuff. All right, so I'll see you in the next lecture.